Okay, so we have one more theorem just to follow the previous result for this subsection. So the theorem is by Riesz. So what the theorem says is if we know a sequence of functions converge to a function f in measure, then this fk has a convergent subsequence and they converge to f almost everywhere. Okay, so this is in connection with the previous theorem, and also I recall that previously we showed that if a sequence converges almost everywhere, then and also the set E has a bounded measure, then we can show the sequence also converge to that function in measure. But this is kind of the reverse of that. But we cannot get as strong as that result. Instead, we cannot really show this a sequence converge to f almost everywhere just by using this converging measure. But instead, we can only show a subsequence of fk. There exists a subsequence of fk that converges to f almost everywhere. Okay, so the proof actually is not difficult. It's actually it's byproduct of the proof we did for the previous theorem. So here is a proof. I recall in the previous theorem, by that I mean we showed that a sequence is Cauchy in measure if actually is if and only if that there exists some function f that f converges to f in measure. Right? Cauchy in measure means that's convergence in measure. That's the result we know, and we did the proof for this direction. We proved that if the sequence is a Cauchy measure, then it must have. So we showed the other direction. We showed this direction. We showed that if the sequence is a Cauchy measure, then there must be some function f such that the sequence converges in measure to it. Well, when we prove this, recall what we did is we first find the subsequence of this fk, and we show that this subsequence converges to some function almost everywhere. And we also show that this sequence converges to that function in measure, right? And then this subsequence that I just mentioned, which converges to some function in measure and also almost everywhere, it will drag this entire sequence to that limit. Right? That's the idea of the proof from the last lecture. And we're going to use this result during the proof since this sequence converges to f in measure, so we know that this is a Cauchy measure. Okay? And then we know that there exists a subsequence of this fk, and we denote it by fki. And it will converge to some function, we call it g. It converges to g in measure, and also it converges to g almost everywhere. Right? This is the result this is the part of the proof for this theorem. Okay, and now we're almost done because we found the subsequence of fk, and we call it fki, and we know that they converge to g in measure. At the same time, this fk is just a subset or just subsequence of f. This fki is just a subsequence of fk, and so it should also converge to f in measure. See, it converges to g in measure and also converges to f in measure. And we know that convergence in measure has a unique limit in the sense of if you identify two functions that are equal almost everywhere, and that means this f and g are actually equal almost everywhere. Okay, and this means that this g is just f. It's equal to f almost everywhere. And if you know this, and you know that fki converge to f almost everywhere, right? Because fg are equal almost everywhere. So that means this fk converge to this f almost everywhere. And that is the claim we just made. Right? So that's the proof. As I said, it's basically a byproduct of the theorem or the proof we did for this previous theorem. Okay. So before I move on to the next subsection, I want to give a brief summary of what we have for convergence of functions or sequence of functions. So recall we have seen different types of convergence so far. But what are related to measure theory is mostly three types of convergence. First type is called, let me call it summary. First type is the convergence almost everywhere. We denote it by this, right? And this is a slightly weaker version than convergence pointwise, because this is basically pointwise, except for a measure zero set, right? So this is really not too much different, just slightly weaker than convergence pointwise. Okay, so this is the first type. Let me make a frame of it. Another type is convergence in measure. This is what we have been doing in the last lecture. So we denote this convergence in measure by this, right? Okay, and lastly, we also have a weird definition from the Agorov theorem, which says that Fk converges to F uniformly, but it's not actually uniformly, it's almost uniformly. So I say it is almost uniformly. Okay, and by this we mean for any delta, we can find a E delta which has a measure less than delta, such that the function Fk, the sequence of functions Fk, converges to F uniformly outside of E delta, or in E minus E delta, right? That's the what we said by convergence almost uniformly. Okay, so we have these three types of convergence. So what is the relation between them? We actually reviewed some of the relations earlier. And here I'm just going to give you a summary of that. So let me use arrows to indicate implications. Okay, so let me first do this. Then I will make connection of the bottom two. All right, so let's see. We know that if so all these functions are defined on E. Okay. We can consider them to possibly have infinite value, or taking value infinity somewhere. But let's say that for simplicity, or for which is general enough. The case that's general enough is that the functions are finite almost like everywhere. Okay, so if it's infinite, then only happens on measure zero set. We don't really care about that part. But in general, we can have this and assume that it's finite almost everywhere. And this E here, by the way, this E is always a measurable set throughout. I think throughout this chapter and the following chapters. We only consider functions defined on E, where E is measurable. Okay, it's a measurable or Lebesgue measurable subset of Rn. Okay, because otherwise, the function, if E is not measurable, then the function f is very likely to be non-measurable, and we cannot do anything with them. Right, so we assume this E is measurable. All right, so from convergence almost everywhere to convergence in measure, we prove that we think that this is stronger. Right? This is stronger than this. Okay. The reason is that we can easily imply we can easily get this one from here. Okay. So this one is easy, but only under one condition that we can immediately get that is that the measure of E must be finite. Okay, so this includes two cases. The E could be bounded or could be unbounded. If E is bounded, then the measure must be bounded. But it's also possible that a set E is unbounded, but still measure is bounded. For example, if E is just a collection of rational numbers, or collection of natural numbers. So the measure of E is 0, but the set E itself is unbounded, right? So this is not as strong as E is bounded, but if it's E bounded, then it's just it must be true. Okay, so we proved this one earlier. Let's see what we have proved. But the other part, and then think here, this direction, from the fact that FK converges to F almost everywhere, we know this is true by the Agraff's theorem. But that theorem also requires this measure to be bounded. Okay, so this is by Agraff's theorem. Okay, so this you have this direction, then basically we have if you have this direction, if you have this direction, then it's like the converse of the Agraff's theorem, and that's not easy. That's not difficult to show at all. I gave this as one of the homework problems in homework 3. That's you can show it by yourself. It's pretty easy, and not only that, actually, it doesn't require any condition, because even if the measure of E is unbounded, so I'm writing it in this way, means that the measure of E could be finite or could be infinite. We can always get this direction. Okay, we can always get this direction. So it's like that. This one is pretty strong. It's even stronger than that. So that's why we can get the implications. And actually, in practice, this is even too strong to imply that. Maybe we can get this even weaker. We can say they converge to never mind. It can be easier, but I think when you do the proof, you can see that. When you do the proof, you can see that this is not this even. This is we don't really need this. We can use an even weaker one of this. Okay. But this is this direction we show by the homework. And now let's see. This is the only one left. Well, as we said, this is generally stronger than that, so we don't really expect this one to imply this. Well, the Riesz theorem above actually shows this, but in a very weak sense. It says that only if we can only find a subsequence. So if we know this convergence in measure, we can only say there is a subsequence converge to that. But the good thing is that we don't require the E to have a finite measure. So E could still have an infinite measure, but we only have subsequence convergence. Okay, only have subsequence converge. Just say converge almost everywhere, and this is by the Riesz. Okay, so that connects these three. And now you may wonder what happens between the bottom two. Well, if you have seen diagrams in mathematics, you probably know that we can just go this direction. Instead of going here, I can just go this direction, right? And also going back forth, I can just go this direction. But this could get some. We could lose something in between, because when you go from here to here, this probably lose some of the properties of this one. It's not equivalent, so we may lose some properties here, and then we imply that, and we still miss something. So one of the things is this, right? Because from here to here, we don't require E to be anything, right? There's no requirement on E. E could have finite measure or infinite measure, but from here to here, then we need a finite measure. The question is that can we get directly to this without any requirement on E? And the answer is positive, which is the one I'm going to show you soon later. So this one is always true. even if E has an unbounded measure. Going backward is not straightforward. It's actually this direction. So itself doesn't imply this at all. Okay, it does. The reason is because you can recall the example we gave before. You have this function that takes 1 initially, and then just take 1/2 here, and then 1/2 here, and then 1/4 of those. You know that this function is not. It's only convergence in matter. It's not converge. It doesn't converge almost everywhere. And if it doesn't converge almost everywhere, it cannot be converge. It cannot converge almost uniformly, because otherwise it will be converged almost everywhere, since this already implies that, right? So we don't expect this direction to happen at all. So in generally, this should be false, but we can still go this route. Going for this route, you see the specialty is here. From this arrow requires, or we can only get subsequence convergence, or convergence subsequence going this route, right? And then once we reach to here, then we can get here if we also have the boundedness of the measure E. Okay, so this is the only way that we can get through at this moment. All right, so that's the whole picture here. And as I just mentioned, I'm going to show you this one, which means that if the sequence of functions converge to f almost uniformly, then they will converge to f in measure. Okay, so okay, so as I said, this is the one I'm going to show. And if we can show this, then we don't need to go this route, because we're going to lose. We're going to make the condition stronger here. Okay, but as I said, we can just directly go. Okay, the proof is actually not difficult. Recall that to prove the sequence of functions converge to f in measure, we just need to show that for any epsilon delta, the measure of ek epsilon is less than delta. Recall this ek epsilon is the set of points where, use this notation, it's where this fk x minus f of x is bigger than or equal to epsilon, right? That's the definition for ek epsilon that we have been using for many times now. Okay, so this is the only thing that we need to prove. Well, to prove this, say for any epsilon and delta, I know first that there exists, we have this convergence almost uniformly, means that there exists some E delta such that the measure of E delta is less than delta, right? That's one thing. The other thing is that over this E minus E delta, or over the E delta complement, we know the sequence converge to F uniformly. Okay, and that means there exists some K, which is a natural number, such that the Fkx minus f of x is less than epsilon for all the x in E minus E delta, and also for all the k bigger than or equal to capital K, right? The convergence uniformly over E minus E delta. Okay, so what this means is if x belongs to, so if x belongs to E minus E delta, and then that means x is in E k epsilon complement, right? Because ek epsilon itself is where the the difference between these two is bigger than epsilon, bigger than or equal to epsilon. But now, if x is in here, I know that this is true. If this is true, that means x is not in the E. It's not in this set. It's not in this ek epsilon, right? That means x is in the complement of ek epsilon. Okay, for any k, because k is arbitrary, it's greater than or equal to k. All right. And so what this also tells us is that since for any point in E minus E delta, we show that it's in ek epsilon complement, I know that E minus E delta, which I just denoted by E delta complement, is inside ek epsilon complement. And this means that ek epsilon itself is a subset of E delta, right? We just take the complement on both sides. It will change the direction of the inclusion, right? And now, as you can see, this is true for all the k. Okay. Sorry. Here, this is what the so I should complement here. We need to show that for any epsilon and delta, there exists capital K, such that this is true for all the k bigger than or equal to capital K. Right? So that's actually what we already got here, because we showed that the measure of E k epsilon is a subset of E delta. So the measure is less than or equal to mu of E delta. And we know that the E delta has a measure delta. And this is true for all the k bigger than or equal to capital K. And that it completes the proof, because for any epsilon delta greater than 0, we found this ek such that this measure is less than delta for all the k bigger than or equal to capital K. So that completes the proof here. And it doesn't require anything on the set E. E could have finite measure or could have infinite measure. Okay, so that's the summary of the 3 types of convergence we learned so far. Okay. Now, next step we're going to consider or talk about the relation between measurable functions and the continuous functions. Apparently, measurable functions is much more general, right? We said that any continuous function is also a measurable function. The question is, can we how general or how much difference between the two? And this is the thing that we're going to cover in this subsection. Okay, so it's actually the relation between the two is reviewed by a very interesting theorem. Called Lusin's theorem. Okay, so what the theorem says is that if you have a function f that is defined, is a measurable function, again, as we said earlier, this E is measurable set. It's a measurable function, and it's finite almost everywhere. Okay, so you could take infinite value infinity, but it only happens on a measure 0 set. Then we actually can show that this function f must be almost continuous. The almost is the same meaning as the almost uniformly. Okay, and here is the actual definition for almost continuity. So that means for any delta, there exists used to have a f delta, but let's say I'm going to consider a closed set here. F is closed, and also the measure of E minus F. So this E minus F is like the E delta before. It has a measure less than delta. So that means the F is almost as large as E. The difference is less than delta. But this delta is arbitrary. So you can set delta in advance. Can be arbitrarily small, positive and small. And then we can fill up this E using this F. So F is almost as large as E, although it's just a subset of E. And over this F, the function is continuous. Okay, so you can see this is a kind of surprising result so far, because we know the measurable functions are much more general, or can be really weird or strange compared to continuous functions. But the Lusin's theorem says that if you really have a measurable function that is finite almost everywhere, then it's just almost continuous as well. And by that, we mean that you can consider just restrict your F to a slightly smaller closed set inside E, and this F will be continuous over the entire F, right? Over the entire closed set F. Okay, so that's why I said this is almost continuous over the F, over the E. Okay, means that it's continuous over F, which is pretty much as large as E. Okay, so let's see the proof. So apparently, we don't really need to consider the set where function f is infinite, right? So without loss of generality, we consider the case that f is just finite everywhere. This is because the measure where f is infinity is just equal to 0. Okay. By the way, I sometimes write in this way. This is just a shortcut for this. Okay. It's just much easier to write in this way, and this just means the set of points where f is infinite. Okay, so we just need to consider a function that is finite everywhere, and to prove this, we first show a simpler case where f is simple. Okay. It's a simple function. So by simple, we mean that the f can be written as a finite sum of piecewise constant functions, which we write as ci ei of x. And we know this ei is a disjoint, makes a disjoint union of E. Okay, just that the union of them is E, and they are mutually disjoint. The EIs are mutually disjoint. Right, this is a simple function. It's basically a piecewise constant function. Well, so from here, we know that again, by the way, that all those sets are measurable, right? That's how we define a measurable function. We need this to be measurable, EIs to be measurable, for this f to be a measurable simple function. Okay, so assume those sets are measurable. Well, if it's measurable, we know for every I, there exists a subset. We call it Fi. Let's see, Fi is closed. Such that the measure of EI minus Fi is less than delta over P. Okay, so P is the number of partitions of E. Okay, so we have E1 through EP as a partition of E. Okay, and why this is true is because recall that for any measurable set, we can find on one side we can find a open set that can be arbitrarily close to EI to this measurable set. Right, that's the one of the result we showed before. If we have a set E that is measurable, and then that means there is for any delta, there exists open G such that the E is included in G, and the measure of E or measure of G minus E is less than delta. Okay, and we can also show easily the other side. There also exists a closed set such that the F is included in E, and the measure of E minus F is less than delta. And now I'm just making E, and just substitute E by EI and F by Fi, and here I require it to be delta over P. That's the difference. Okay. So for measurable sets we can, do this. All right. So that's the EIs that we find, and remember that the FIs we found. Remember the EIs are disjoint, so the FIs are disjoint as well, because each the FI is included in each in one of these EIs. So the FIs must be disjoint as well. Okay, you see why we need this F to be closed. But at the moment, you can see the union of those FIs will have a measure less than delta, because the difference between EI and FI is less than delta over P. So the union of them will be just we'll have a measure that is close to E and difference is less than delta. Okay, apparently, so this taking the union of this fundamentally closed set, the F is closed, and at the same time, the measure of E minus F is less than delta. Okay, and to show this is not really difficult. You just recall that this E minus F is what? Put it online. This is because mu of E minus F is the same as mu of E intersection of the F complement, and that is equal to the measure of the mu, the EI taking the intersection of the union of FIs, I from 1 to P complement. Okay, so this can be written, be written as, maybe I should skip just the middle step, because this is just the union of EI minus FI as from 1 to P. The reason is that each FI is included only in EI. Okay, so only inside EI. So when you take this difference, the Fi is making the difference of this. Okay, and this is less than equal to the sum from 1 to P the measure of mu ei minus fi, and we know this each one of them is equal to delta over p, so total will be just delta. Okay, and we actually have this. This is less than. Okay, so this is what how we get to here. And now I'm going to show that this function f is actually continuous over this set f. Okay, to show that, we know that for any, if we want to show the function f is continuous at a point, we just need to show that the function, if the point is a limit point, we just need to show that any sequence converging to this limit point will have their function value converging to the function value at that point, right? Recall that f continues if and only if that for any sequence xk where xk convert to x, we know f of xk convert to f of x, right? That's the continuity. What the continuity means in the Euclidean space. In Euclidean space. And you can see that this means that x is a limit point of xk. Okay, and this is why we need the closed set earlier. And this f is closed, and each of this fi is closed, because when we consider a sequence converging to a limit point x, then we know that we're restricting ourselves to a certain fi, right? Because fi contains all its limit points. So if you have xk converging to x, then you know that x must be inside the same set of xk. Okay, and you cannot have x. You could have xk belonging to different fi's, but if they really converge, then you know this xk, there must be one of these fi that has infinite many of these xk's. That means fi will some of those xi's will contain a subsequence of xk, and because fi is closed, and the subsequence convert to x as well. That means x is also in fi. Okay, so for any point for any limit point, it will be inside one of these fi's, and it can only be in one of those, because those fi's are disjoint. It can only be in one of them. So it will be in one and only one of those fi's, and we can consider the convergence of this over that specific fi. Okay, where this x belongs to. Okay, but over that fi. Okay. The x is in that fi, and if xk convert to x, let's say just without loss of generality, as we said, you can always consider this set to be in fi. Then we know this f of xi, they are all equal to ci, because there are points in fi, and fi is a subset of ei, and over the ei, the function takes the value of ci, a constant ci, and that's why this apparently just convert to ci, right? For k going to for k going to infinity, because every point is just taking the same value, ci. Okay, and apparently this means f is continuous at x. Okay, and then we show that for every point in f, the function is continuous over that at that point x. That means just f is continuous over the entire set f. Okay, and this f is almost as large as the set E, as we showed earlier, because the differences can be arbitrarily small. Okay, this is how we show that the statement is true for simple functions. But we need to show this for general measurable function, right? And this is what we're going to continue the proof. Okay, next we're going to show that this is also true for general functions. Okay, without loss of generality, I'm going to assume this function is uniformly bounded. Uniformly bounded by 1. The reason is I can always make this transformation of f. This is because the function phi of y as y over 1 plus the absolute value of y is always between -1 and 1 for any y, right? This phi, I can also show that this phi is a let's say it's a one-to-one correspondence. And it's really increasing. It's one-to-one. It's really increasing. So this phi is continuous. The f inverse also exists and also continues. The phi inverse of y is equal to y over 1 minus y. Okay, and it's pretty easy to show this. And what the reason why we introduce this phi is because if f is not uniformly bounded, and we just consider phi of f, or the phi composition of f. And once we can prove the phi composition of f, phi and f is continuous, then we just need to take another composition of phi, and then this will give us the f back. But this part, if we can show this is continuous, then this is absolute. This is also continuous. The composition of these two, which is equal to f, will be also continuous, right? That's why we can assume that function f is uniformly bounded by, if it's not, just to do this kind of transformation, which is continuous. All right, so now we just work on the case where f is uniformly bounded. And now, because f is uniformly bounded, we know there exists a sequence of simple functions fk such that the fk goes to f uniformly. It converges to f uniformly. Okay, uniformly on E. Okay, so why is that? Actually, this is what we proved before. Recall that f can be written as f plus and f minus, right? Can be written as this. Well, we can just show that there is a non-decreasing sequence of simple functions. We call them, say, fk plus. This will be simple functions, non-negative simple functions, and they are non-decreasing, and they go up to, so non-negative simple functions fk, and they will convert to f plus uniformly, right? This is all because of the construction we did before. If you have this as your f plus, recall that if this is a big M, actually this is a 1 right now, but let's say this is general big M, then we can partition this into, we first consider the entire M, and then we partition this m into 2 parts and then 4 parts, right? And then 8 parts, 8 equal parts. And for each one of them, I will consider, for each one of them, I will set this, let's just say general function, simple function f. If I'm given a non-negative function f, then I'm going to just define the fk, phi k of x to be if f of x is between, is bigger than, recall that is 2 to the k over j minus 1 over 2 to the k, less than 2 to the k and j, then I'm going to define this function to have the value j minus 1 over k, right? That's what we did before. Right? And this should be, let's say m is big K. What do we use this big K? And then we partition this big 0 to K into, remember that's K times 2 to the power K segments, equal segments. And each one will have a length 1 over 2 to the K. And so that means I partition this into this many equal segments. And then we take the lower bound of the function value over this. So that's how we get that. Now we also have another part where function f is bigger than k. But right now, assuming that function is uniformly bounded, I know that there exists some k such that everything is bounded, is below this k, right? So I will have, I don't need to really have this part, but just define my phi k x to be this if the function value is between that. Okay, now you can see that phi k is always below f, but it's getting closer and closer to f. The difference between the two, the phi k x, the difference between these two is always less than j over 1 over 2 to k for any x, and that's why we can show that the phi k converges to f uniformly. Right? And that's the reason why we can get a sequence of non-negative simple functions, and they convert to f uniformly. They're actually non-decreasing, and they convert to f uniformly. And this, for f plus, we can get this. And for f minus, we can get another sequence. So the difference of the corresponding sequence terms can have this, right? Then f plus, fk plus minus fk minus will be also converging to f plus minus f minus, which is equal to f uniformly. Okay, and that is why we're making this claim here. Okay, so this is just the part we proved before. In case you have you didn't remember it, just say that's the case. All right, here, so we have the sequence of simple function fk convert to f, and now for each of this fk, I know there exists a closed subset fk that is a subset of E such that the measure of E minus fk is bounded by 2 over delta over 2 to the k, such that such that this is the difference, the measure of the difference is less than that, and fk is continuous on this set capital Fk. Remember that this fk is just a subset of E, so the sequence is still, if the sequence fk is converging to f uniformly over E, it must be overall converging to f uniformly over this fk, right? Just a subset. And on the other hand, when we take f to be the intersection of those fk's, And it would be easy to show this f is still closed because it's just intersection of a closed set, right? Intersection of closed sets. So it's still closed, and the measure of f, or measure of E minus f, is less than delta. And this can be easily shown by the fact that this is a E minus intersection of fk. And you can easily show that this is just the union of E minus fk. And that's less than or equal to the sum by the subadditivity of measures. And we know that each one of these measure is less than delta over 2 to the k, so in total this is less than delta. Okay. Okay, we have this sequence now. We know that they converge to f almost uniformly over the E, and now we restrict to each fk. If each of this fk to this set, closed set fk, we know the fk is continuous. Okay, fk is continuous on that. So if we take the intersection of this fk, we know that fk will be continuous over the f. So fk is continuous over the f, since f is the intersection of this. So it's a subset of fk. Okay? And the fk converge to f uniformly on this f, because uniformly on E, and f is just a subset of E, so this is also true. And I recall that if you have a sequence of functions, a sequence of continuous functions, and they converge to some function uniformly, then the limit function must be continuous as well, right? This is one of the results in analysis. And I think I also gave you this question in the first homework to check your prerequisite for that. And this just directly implies that f is continuous. Okay. All right. So that's it's continuous on f, and that completes the proof right here. We said for uniformly bounded function, that for general uniformly bounded measurable function, we can show that it's continuous over a closed set f, and this f is not much different from the set E, because their difference can be, the measure of their difference can be arbitrarily small. And that completes the proof here. Okay, for this Lusin's theorem. Okay, and in summary, what we have here is that if the function is finite almost everywhere, then it's just almost continuous. Okay, you can take out a arbitrarily small set with positive measure, and the remainder set is closed, and the function f is continuous over that closed set. All right, so that's the Lusin's theorem, and from that we can get two results, two corollaries. The first one is that if f is finite almost everywhere, then finite delta, there exists E delta, or let's just there exists some continuous function such that the measure of sets where they do not agree is less than delta. Okay, so that means you can find arbitrarily small set, a small measure delta, and the f will agree with the g will there will be a continuous function g that agrees with f outside outside of that tiny set. Okay, or in other words, the f, there will be a continuous function g that agrees with f almost inside the entire E, just missing a slight positive measure set. Okay. Okay, and the proof is actually that's just the same as before. We know that we can find by the previous theorem. We know that there exists a closed set of E such that the E minus F has a measure less than delta, and at the same time this F is continuous on this subset F, right? So we just define a G which is continuous on this F, and we can extend the G to the E minus F continuously. Well, this actually needs some proof why we can extend a function continuously to a larger set. This actually needs some proof, but I think it's not. The proof itself is not. It's not universal. It doesn't apply to any other result. Just apply to the case here, to this particular situation. And so I will just give that proof. You just admit that if you have say you have a set E, and you have this subset they are both measurable, and you have function that is continuous over the F, then they can be extended continuously to the entire E. That means you have the function G defined on this set. Then you can find another function F such that when you restrict it to the set F is equal to G, and F is continuous over the entire E. Okay, here G just continues over the set F, subset F. Okay, you just admit this is true. All right, and then in this case, you can see that we just define G to be the same as F over the set F, and we'll continuously extend G to the outside of F. Okay, then as you can see, where it is not, the only place that they do not match is only in E minus F. So the measure of the set where G is not equal to F must be less than or equal to the measure of E minus F, because over F they are equal. Okay, they can only be different over E minus F, and this is less than delta. Okay, so that's the corollary here. Another corollary which is more important is that, again, assuming that F is a measurable function that is finite almost everywhere on E, then there exists a sequence of continuous functions, gk, such that the gk converges to F almost everywhere. Okay, and the proof of this is not difficult either. Consider the two numerical sequences, delta k and epsilon k. They are positive, then goes down to 0. And then for any k, I know that we can find there is a function, as in the previous corollary, there exists a continuous function gk from E to R, such that this gk will agree with F over a set. So let me just continue here. Exists a ek me just even say just fk would be fine. Fk close the set. Such that the gk is equal to f on this fk, and therefore the measure of the set of f minus gk is bigger than equal to epsilon k, is equal to the measure, is less than equal to the measure of f minus gk greater than 0, right? And this is the where this must be a subset of E minus Fk. As we said, the two functions match or they agree over Ek, and this is less than delta K. Okay, so what this shows us is that for any decreasing sequence, just find any decreasing sequence, a positive decreasing sequence, and we can show that this is true. Okay, and now you can see that this f gk, this gk will convert to f uniformly, right? Sorry, converts to f in measure, right? So the gk convert to f in measure, right? And hence, recall the Riesz theorem above. There exists a subsequence gki that convert to f almost everywhere. Okay, and recall that each of this gk is continuous function. So I just extracted a convergent, a subsequence of a sequence of continuous functions, and I will show that the subsequence of functions, they converge to the function f almost everywhere. Okay, and then go back to the, just in summary, what we did in this corollary is that as long as the function f is measurable and is found almost everywhere, then we can show that there exists a sequence of continuous functions that they convert to f almost everywhere. This is actually important later on because we can, what this means is that for any measurable function, we can approach it or approximate it using a sequence of continuous functions. Okay? So the measurable function itself can be really strange, may not be continuous, could be very strange function, but we showed that it can be approximated by a sequence of functions, a sequence of continuous functions. Okay. Okay, so the last topic we're going to talk about is the measurability of composite functions or the compositional functions. We show that we may wonder that if we have two measurable functions, we make composition of them. Is the result still measurable? Okay, it's a very natural question. Unfortunately, this is not true. To prove that, we give a series of the results below. So for example, suppose f is a mapping, then f is measurable if and only if for any open set, the pre-image or the inverse image is a measurable set. for any open. Okay. So the proof, the claim here is that the function f is measurable if and only if the pre-image of any open set is measurable. Okay, and this is the sufficiency is very easy because we know that by definition f is invertible, f is measurable if the pre-image of this interval is measurable, right? And now this is open. This interval is open, and if this is open, this is a measurable for any open set G, then this is a measurable, right? Because it's just a special case of open set, and that means this f is measurable. Okay, so this is just because that is measurable with the right, this has this. Okay, so that's that direction, and the other direction is that if f is measurable, then how do we show that G this is true? How do we show this is true? Actually, the first thing that I didn't mention this before, or actually prove this before, is that if you have an open set G that's in R, just in R, then this G is a union of at most countably many open intervals. Okay, if G is open, means that there exists k open intervals where GKs are disjoint such that G just equal to the union of those IKs, the intervals. So you could have finite many of those intervals, or could have at most countably many of them. The reason is, well, it's not hard to prove. It's just the proof itself is a little bit tedious, but the idea is really simple. Let me show the idea here. The idea is that if you have this set of this R, let's say R, and so you have an open set over this open subset G in this R, and then we'll just look at any point in G. Say this X, if this X is in G, it belongs to G, then what you are going to do is to just look at all the points that is connected to X. Let's say I can define a E related to X to be the collection of points Y as in G, and the entire interval X and Y is in G. Okay, so what this means is for any other point Y, I will include it into this EX if everything in here is also inside G. Okay, so that means this part of the interval, this continuous interval here, is also inside some larger interval inside G. Okay, and now you can take the supremum of this and also take the infimum of this. Then you just keep expanding this until you reach to the point where the point is not in G anymore. And then this will be an interval, right? And for every point you can do this. Then maybe another point here you can expand it, and you have another interval here. So eventually you will just have disjoint open intervals in G. And the question is if this union of these intervals must be G. The only question left is that if there are at most countably many of those intervals. And the answer is yes, because for each of these interval, we can find a rational number to represent this interval. And then we can establish a one-to-one correspondence between these disjoint intervals and a subset of rational numbers. But rational numbers, the set of rational numbers itself is countable. So these intervals will be also countable, or at most countable. So that's why we could have just finite many of these intervals ik's, or at most countably many of them. So if G is open, then we must be able to write it or present it in this way, just a union of open intervals. Okay, so the proof itself, you write it out, it will be tedious, but the idea is just as simple as this. Okay, so let's assume this is true, and we're going to use this here. Assume that f is measurable, then I know that for each interval, open interval in R, I know that f inverse, the inverse image of this interval should be equal to the inverse image of this minus the inverse image of this, right? But we know that both of these two sets are measurable, so their difference is also measurable, right? Each of them is measurable because f is a measurable function. So this is a measurable set, this is a measurable set, so the difference is measurable, and that means this is measurable, which means this is measurable. Okay, and as we just showed, since G is open, and that can be written as a union of at most countably many open intervals. So we know the F inverse of G, or the preimage of G, is just the preimage of this union, and that is just equal to the union of the preimages, and each ik is like this kind of thing. So that's why we're just taking the union of measurable sets. So this is still measurable. Okay, so that shows the other direction. Okay, so all it actually uses is just the fact that G can be written as this kind of union of open intervals. Okay,